Okay, so let's go into part 2 of the labs, which cover input-output and peripherals. It's labs 5 to 10. In lab 5, we show how to create a Vivado project in order to create the bit stream that we have been using today. Vivado is a silence tool for viewing, modifying, and synthesizing the source code for the RVfpga system. You can find the source code here at RVfpga src. Here you have all the modules that make up the system on chip. And in this lab, users create a Vivado project that contains the RVfpga system source code, synthesize it targeted to the Nexus A7 board, and create a bit file that contains information to run the system on chip on the board. Vivado is used extensively in labs from 6 to 20 for modifying and simulating the RVfpga system. Lab 6 starts introducing input-output, and it uses a general purpose input-output communicating with the switches and LEDs that you've already used in the example LED switches and that we explain in detail in this lab. We start with a simplified theoretical version of a generic GPIO controller, and then we explain the one that we use in SwearWolf, in the system on chip that we use in RVfpga. And in these labs, from 6 to 10, we always use the same structure. So we first analyze the high-level specification and introduce fundamental exercises. And then we analyze the low-level implementation of the device that we are analyzing and introduce advanced exercises. You'll see this structure in all these labs. This is the introduction to a generic GPIO controller. It includes 3 registers, as you all probably know, a read register, a write register, and an enable register, so that each pin can be configured as an output or an input. And this is the GPIO module that we use in RVfpga. It's obtained from OpenCores, it's open source, and allows up to 32 GPIO pins, which is perfect for us because we have 16 switches and 16 LEDs. So this is the memory map that we use for for the 3 registers within the GPIO module. The read register is mapped to this address, write register, and enable register. So taking this into account, we can configure these peripherals, the switches and LEDs, using the GPIO by writing to the enable register this number, which is 16 zeros followed by 16 ones, because the LEDs on the board are connected to the 16 rightmost pins, and the 16 switches are connected to the leftmost pins. So we have to configure as an input the 16 leftmost pins, and as output the 16 rightmost pins. We do this in assembly by using these 3 instructions, which write to the enable register mapped to this address. And then we can write the LEDs and read the switches by writing or reading the corresponding registers. So going back to the LED switches example that you executed at the beginning, we can now understand how it's programmed. This is the C version. You have the corresponding assembly version if you want to look at it. So we configure the enable register. Note that we have 2 macros, one for reading an address and one for writing an address. And we have these addresses for the switches, the LEDs, and the enable register. So in our function, we first configure the enable register with the LEDs configured as inputs and the switches configured as outputs. And then we stay in an infinite loop where we read the switches and write their value to the LEDs. Okay? So this is the program that you tested before called LED Switches program. In the second part, we explain the low-level details of the GPIO controller. So we explain how it's connected with the board, how it's connected, how the controller works, and how it is connected with the Swerve VH1 core through a multiplexer that selects, based on the address, which peripheral to use. Okay? Let me show you the Verilog files as an example. You can take a look on your own later if you want, but let me show you. Those of you who are familiar with FPGAs, you know that there's a constraint file that determines how the connections are made with the board. Okay, so this is the constraints file for our project. We have the switches, 16 switches here, 16 LEDs here. We also have the 7-segment displays, as we explained in Lab 7, and also an accelerometer, as we explained in Lab 10. Okay? So this would be the connection of the GPIO with the board, okay, this part. We also can view the controller. This is the instantiation of the module that implements the controller. Let me do it a bit bigger. This is the GPIO module downloaded from OpenCores, and we instantiate it from one module in our system on chip, which you can access and you can view. And these are the 3 state buffers that we include for making each pin output or input as determined by the enable register. It's just to show this that you can view it. I'm not going into details because it would take a long time. And finally, this is the GPIO controller. You can see that it's very big program. This has been downloaded from OpenCores, and you can analyze it as you want, or even simulate and analyze the signals that make this up. So with this, we have covered this part, the controller. Finally, we can view this multiplexer and how the controller is connected with the core. And, well, this is Verilog. This is the multiplexer that we use. We have the memory map of each of the peripherals that we include in our system on chip. And these are the signals that go into the core or that come from the core so that we can read and write the registers within the controller. Okay? Too much to view in a couple of minutes, but well, you can analyze it slowly if you want. So let's do another hands-on activity from Lab 6. And this, I think, is quite interesting because in exercise 3, we ask students to expand the RVfpga Nexus to support the 5 onboard push buttons. Okay? Those 5 buttons are available on the board, but are not supported by the original system on chip that we provide and that we've been using. So as an exercise, we ask the students to modify the Verilog files in order to include another GPIO and communicate it with the buttons. Okay? Obviously, we're not doing this here. We are providing the bit stream, but we're going to test it on a program that uses the push buttons. Okay? So you have the guidance for that in your documents. The idea is to write a C program that displays an increasingly incrementing binary count on the LEDs starting at 1, and to include an empty loop for waiting between displaying each incremented value. And finally, to use one of the buttons to change the speed of the count and another button to restart the count whenever it is pressed. As an addition, I propose you to use a third button for making other functions, such as making the binary count increment by 2 instead of 1 by 1, or whatever other functionality that you want. This, you can do it from the program that we are providing. All the instructions are explained in the document. You can find there the project that includes this program, also the bit stream with the modified controller, okay? And then you can try to add this new functionality for the program, okay? So try to do it and ask me if you have any questions.